Great, man. Thank you. Hello, everybody. Welcome to our talk on conquering all stores. My name is Vladimir Bacvanski. I'm principal architect with software architecture. And I'm here with my colleagues, Deepak and Anisha, who will introduce themselves when they get to their section. So let's go to the next slide and let's see what is that we are going to talk about. So we are going to start giving a little bit of the background and then figure out why do we need this system that is providing uniform access to a variety of data stores. And then Deepak and Anisha are going to show you some lower level details, including some interesting Scala code, and then we'll discuss the future. So let's go to the next slide. So thinking about PayPal, PayPal, as you know, is in payments, and we have a large number of customers, and also PayPal is growing both organically, but there are also acquisitions. And you all know Venmo, but there are other groups and companies that we have acquired. And what is interesting, when you look at the numbers that all of these things contribute to, 360 million customers, there is significant payment value, and there is a large number of transactions that are happening. So when you look into the ecosystem that we have, and the ecosystem consists of the core PayPal, but then there are a number of, how we call them, adjacencies, Venmo, Zooms, and so on. And they create very large amounts of data that we want to analyze and gain insights. So PayPal was running a large number of Hadoop clusters. We have over 20 on-premise clusters, and now we are migrating to Google Cloud. 200,000 yarn jobs a day, over 160 petabytes of data, and rapidly growing. And some of the largest installations of Oracle, Hortonworks, Teradata, and Aerospike, which is the key value store. To add to that, there is such a variety of processing that is working over these data stores, from conventional Hadoop and Hive to Spark and so on. So here is the big picture that is showing the landscape. In the lower area, you have sections that are showing the data centers. And in fact, we are running across multiple data centers in different geographic regions. And we are now in the process of migrating more and more of our activities in the public cloud. And the interesting thing here is that our infrastructure is kind of a smart, and it is using various mechanisms to predict the required allocation so we can move and shift the processing where it is needed. There is also a strong emphasis on redundancy, because when you are in a financial world, reliability is very important. Then on top of that raw infrastructure layer, there is a variety of data stores. From your traditional big data stores like HBase and processing with files with Hive, but also there are streaming systems, most notably Kafka, very large installation of Kafka with some very high numbers, over 6 million Kafka messages per second. There is also significant text search with Elastic, but also there are stores like Teradata for the data warehousing, and a variety of NoSQL stores like Cassandra, and there is also Druid for our analytic workloads. And the question is, you have a variety of roles that would like to access this data and process. So in the top part of the slide, you see different roles: developers, scientists, analysts, operators. And because we are heavily regulated, on the right-hand side, you see elements of logging and monitoring, alerted, and particularly security is really infused in every little thing that we do. So all of our systems have either native or some added capabilities that would provide such a great level of services. Now, when it comes to processing this data, you want to create an approach that makes these user roles more comfortable and more productive in the use. So in the area of the slide where you see the gears towards the middle left, you see a variety of compute frameworks and APIs. They pre-can some of the developer experiences and the ways of common access. But one of the really interesting and common things, and this is really essential, is this symbol that looks like a book. This is UDC, Universal Data Catalog. This is the meta store for our data. that captures every little thing that you have in a variety of data stores in HDFS files. It has the explanation of the data, the columns, if this is a privacy-related information or highly sensitive information. And the interesting thing is that you can go to the catalog, you can browse, you can search, and this is also the vehicle that drives our compliance efforts in security and privacy, because by inspecting the catalog, you know where are the things. And then the data is accessed through the APIs. For many of the stores, you don't want to allow everybody to run wild queries over them, but you want to have a more controlled access. Now, a little bit over that, in the upper left part, there is a Gimmel SDK. This is the SDK that provides the uniform access to all of these data stores, and all of these stores will appear as the SQL data stores. And this is actually really powerful for our analysts, data scientists, who would otherwise need to know and understand all the details and intricacies of accessing Cassandra versus Druid versus Teradata and so on, which would not be feasible. With this, they have a one way of interacting the system. And one of the really exciting things in this space is trying to create a unified experience for our users through notebooks. So we have the version of Jupyter Notebook that is heavily customized, very much infused with security, and that provides a really nice platform for productive development and experimentations. And with that, I will pass it to Deepak. Thank you.
Thanks, Vladimir. Hi, everyone. This is Deepak. I'm a tech lead in Data Platform Services Organization in PayPal. And I would like to thank you all for taking the time to be here with us. So why Gimel? It's the most important question before we get into the details. As Vladimir mentioned, the payments industry has accelerated. Along with that, PayPal's business has grown tremendously. What this meant is the data has exploded in PayPal, and as you may have seen, we've deployed a plethora of technologies, and data is everywhere. And being a data-driven organization, we would like to make sure the power of data is really leveraged by all kinds of personas, not restricting to specific types of uh, personas. For this, we need to democratize data. So when you look at accessing data that resides in multiple different systems, the access is really cumbersome and fragile. This is a simple boilerplate code to access data in HBase. Back in 2018 and 2019, when we were writing Spark applications to read and write data from different systems, the code used to be something like this. This is a simple example, but it gets complicated when you try to mature this and scale it. Not to really go into the depth of this code, but if you expand on this pattern, the code is really very complex when you look at multiple stores that may be in an ecosystem. Now, even if you take a simple example of working within the realms of Spark as a compute engine, Spark provides multiple form modes to execute your business logic. We could write Spark SQL, Spark batch application, or a Spark streaming application, or even expose the data in the form of APIs by integrating Thrift servers. For the data developers, there is a plethora of options to write their business logic. One could use Spark SQL or choose a language as Python or Scala or Java and then express their logic and then write a Spark application. So you can see the permutation combination keeps getting more and more complicated for somebody who is going to begin working with the data. And this creates a lot of challenges, especially when you look at the data application lifecycle. Let's say we take an example of streaming data from Kafka into HBase. Maybe I'm working with payments data. I need to create a data application that needs to stream live payments data or activities into HBase, and then I do some analytics on top of it and expose the data. As a developer, we tend to go through this life cycle. We learn how to access Kafka, how to access HBase, how to write code in Spark in one version. We then optimize the code, we deploy it, and we run it. But what if the compute version changed? We have evolved from Spark 1.x to 2.x, now in 3.x, just within the Spark realm. So when you look at that migration, the code breaks. Again, the developer needs to learn how to adapt to the new version of Spark and optimize the code if required, and then deploy and run it. But what if the storage API changed? Let's say I'm using a Hortonworks connector for HBase, and then it happened to change an API. That requires me to actually go through the same cycle. And the story is very similar for various other dimensions. If the connector upgraded, it's the same. If the host migrated, PayPal, as Vladimir mentioned, works in the multi-data center hybrid cloud realms. So there is always something changing under the hood. The hosts are being migrated. There is a migration of a particular data store to a new data center, and so on. All of these causes the underlying host names or FQDNs or ports to change. These again result in the breakage in code, which requires us to go through this life cycle. And what if the storage change? Let's say I realize after running the workloads, maybe after a year, that HBase is not the solution any longer. Maybe I need to move to Elasticsearch or another store. I need to rewrite the code. That requires to go through the entire life cycle. But I can
Deepak,
keep
sorry
going.
to interrupt. It seems somebody else is speaking. If you're not presenting, can you please mute yourself? Thank you.
Okay, seems quiet. All right. So the story is same, regardless of what vector or dimension changes. The application lifecycle is very fragile. What this means is, as a data developer or a data scientist who's working with data, or even an analyst, if you write something to work with data, you might have spent 5 to 10% building a business logic. The remaining 90% of the time is really being spent on managing the life cycle of a data application. And when we look at this across the board, across multiple organizations and multiple teams, the time to market and the the potential to leverage data is really reduced because of all the time that we are spending on this life cycle. So we wanted to get to a stage where, as a developer, you should be able to write a code regardless of the changes that happen under the hood. The life cycle should not really affect the application. It should be able to run seamlessly, and we should march on with new data-driven initiatives. So with that, we ended up creating the data API. But before we look into that, let's look at many other factors that play in an organization at PayPal scale. We created a unified data API and a SQL API, which we will be looking at in the coming slides. But once we created these APIs, the other things that started evolving as we deployed our data lake and then started developing big data applications is we needed to gain visibility across all the applications that we're running. So each team or product had their own way of instrumenting things and then having a visibility at their level. But as a platform provider or as a frameworks team, the visibility of the entire ecosystem was missing. And as Vladimir mentioned in the beginning, you may remember there's something called the Unified Data Catalog, which is the enterprise catalog for PayPal, which provides a view of the entire landscape. Now, our applications required to tap into this catalog APIs in the runtime so that they can do many other things like redaction or classification of data to apply security controls. Now, this again posed a problem because each team or application had its own way of integrating with the catalog. And security is ubiquitous. So it's not just within the realms of a store that the security protocols need to work at scale and strength. It's also in an infused way manner in every touch point in PayPal. So we needed to have a Uber security control that we could apply if required. Let's say the GDPR has to be turned on in the entire Hadoop ecosystem, and we need to apply a switch of redaction across all the applications that are accessing some kind of sensitive data. It is going to be a real nightmare because it has to become a program. We have to work with multiple applications. And the other problem that platform providers usually face is Every platform provider, whether it is Kafka or Hadoop or a database admin, they always have the way of instrumenting certain interceptors or libraries that will provide them operable visibilities. So if you think about all these different touch points, which are very common to all the applications that are running, we not only require a unified API to access data, but also we need a unification of instrumenting all these different things that slowly got added over into Gimel, which we will be looking at. Just to double click on one example that I mentioned, if you just take any database or a storage system, and if you want to audit the queries or the application access, there are different means. Teradata has the forms of DBQ logs. You could instrument Eagle for Hive, or there are a bunch of other tools in the industry right now. Oracle has audit tables. I can keep going. But the point is, this way of logging and auditing access is very fragmented, and we don't have a holistic view. Similarly, if you look at the platform providers problem area and double click into it, all these different administrators need to instrument interceptors, and they have to work with the applications to make sure the applications inherit these interceptors and they get the monitoring logs and so on. But from a user perspective, the user has to work with all these different store admins to understand their interceptors, instrument them. Again, the core problem of just working with business logic versus putting all these other ETs on the application is actually in the ratio of 5:95, where 5% is spent on business logic, the 95% goes into all of these other factors. So what if we had a common layer in the form of Gimel, where all these operators can work with Gimel while we inherit all the burden of instrumenting the right interceptors, and we provide a one-stop shop to all the application developers. This works in the benefit of multiple organizations. The platform owners need not work with hundreds of applications, while the hundreds of application developers need not work with every platform owner to make sure they are instrumenting the right things, while we form that partnership or the bridging layer between the two. So putting it all together, if you look from the left side, a data application or a user submits some form of code in the form of a query or in the form of a data API. And that query now, when it goes through the Gimmel application, which is a Spark application, not only provides a unified way of running a code, for example, reading from Kafka, joining with MySQL, writing to Hive, applying transformation can be expressed in the form of a SQL, but also out of the box, we are able to make sure we connect to the classification APIs, see if there are any sensitive elements. If required to turn on redaction, we are able to do that. At the same time, we are able to monitor and alert on the access patterns and provide the interceptors and monitoring capabilities that the platform operators require. We can go beyond this, but the idea is having this unification of API access plus instrumenting all the different requirements that are on the touch points of the ecosystem makes it a one-stop shop, while the data development can accelerate in the ecosystem. Let me just take a quick overview of how the Gimmel API looks like. What is the experience of a developer in our ecosystem when they use the Gimmel APIs? And then followed by that, I will hand over to Anisha. So I'm not going to run a code here in the interest of time, but what I'm doing is I'm on a Google's Dataproc cluster, and I'm running a Spark application with Spark 2.7 and Scala 2.12. Basically, you can observe here that we are going to start a Spark application, and we're going to add the Gimmel API. If you see here, the Gimmel API comes in the form of Scala API. There is a dataset class, or there is a Python API, which can be a simple reference to the Scala class. And the pattern is same. There is a dataset.read API, which provides access to any dataset in the ecosystem. The parameter is you pass a string, which is the logical representation of an object that resides somewhere in the PayPal's ecosystem. And there is an option that you can provide, which allows you to control the behavior of the data API behind the scenes. Similarly, there is a write API which you can use to pass on a data frame through which you can push the data into any sink. It could be BigQuery, it could be Elasticsearch, or it could be Kafka for that matter. But the pattern remains the same. And because we want to make sure our SQL communities are taken care, we have added a SQL abstraction on top of these so that somebody working with SQL could just express the same select clause instead of writing a Java or a Scala or Python code, and also express the same write APIs in the form of insert into, as you may see here. So the quick thing to observe is there is the notion of a data set. There is the notion of the Sparks data frame, which is the main object in the contract, and there are options. So the user now has a simple prescribed pattern to work with any data set or any object in the ecosystem. They could do that through the APIs, which we expose in the form of Scala or Python, or they could actually work through SQL. And the options that the user has in the programming realm can also be exposed to the SQL community by providing them the set options so that they can pass the key value pairs and then work with the data store to tweak the behavior. Now, you might wonder how a string translates to something behind the scene. It works very similar in the way the Sparks unified API works. The only difference here is we have the concept of a catalog provider, where a catalog provider can be unified data catalog in PayPal's ecosystem, or it could be a Hive data catalog, or it could be a user-driven data catalog. Basically, the job of a data catalog or a catalog provider is to supply the configurations at runtime, which will help Gimmel generate the code behind the scene, which connects to any data store. We'll look at the details of how data API works when we get to Anisha's section. So with that, I would like to hand it over to Anisha, who can walk us through the details of Gimel. I just want to quickly show you the code base. After the call, we can go to gimmel.io, and that should take us to the GitHub repo. And there is also a notebook attached here, which I was walking us through. Over to you, Anisha.
Thanks, Deepak. Okay, so hope you are able to see my screen.
Yeah.
Okay, hi everyone, this is Anisha. I am a senior software developer in data platform services in PayPal. Okay, now let's do a deep dive into Gimmel implementation. Okay, so as explained by Deepak before, like in order to read or write from different data storages, a developer has to do some research about different connectors and how to use them in a most efficient way. So in order to solve this problem, Gimmel provides an abstraction by providing a unified API, which is dataset.read and dataset.write. And also SQL access over these data storages, so that not only the application developers, but also the DBAs and product managers who are not aware of the Scala or Java code can also access this data pretty easily. So basically, to summarize, with all the boilerplate code for connecting to different storages is abstracted out here, and developers just need to focus on their business logic. Okay, now let's look at an example of reading from two different storages here, like Kafka and Elasticsearch. So as you can see here, there is a unified connector config, which is passed to the dataset.read API. So these configurations, so in order to change any storage specific property, or if we want to change the data storage itself, we just need to tweak these parameters, and the underlying implementation of dataset.read remains the same. So this gives a flexibility to user to just care about these configurations, but not the underlying implementation of the dataset.read API. Okay, these configurations can be provided to these APIs in different ways through catalog provider. In Gimmel today, we have different options for a catalog provider. First is user. So in this one, the dataset properties are passed as JSON. Well, as you can see here, multiple users accessing the same data set will have to mention the configuration in their applications. So there is no shared repository where these configurations can be stored. And that's why we came up with a Hive catalog provider. With this, all the configurations for these data sets are stored in a shared Hive catalog, so that like it's being shared by different users who want to access the same data set. But still, there can be different Hive clusters, right, in our ecosystem. So in order to maintain these configurations between the different clusters can be challenging. So that's why we came up with an external metadata service option. Here, user can plug in their own implementation of fetching their metadata services in order to fetch the data set from any metadata service if they have. So in a PayPal, as mentioned by Lad and Deepak, we have a unified data catalog which scans all the storages within PayPal and stores the metadata for all the data sets within these storages in a centralized repository. So this is how you can provide your own implementation of you can plug in your own implementation of the metadata service itself. Okay, now let's look at how a Gimmel SQL works. So a SQL can possess a select clause, an insert clause, and also a bunch of set statements to set the runtime properties. Now through a code gen, the select clause is converted into dataset.read call, insert is converted into dataset.write, and all the runtime properties which were set before the SQL are passed on as arguments to these APIs. Once we have the read and write APIs, we call the catalog provider to get the dataset properties for this dataset. Now, based on the storage type attribute of this dataset, the appropriate dataset object is fetched from the dataset factory. And as you can see here, the dataset factory has the storage specific dataset objects. And with each of these storage specific dataset objects have their own implementation of read and write method. And these read and write methods have the core connector implementation. Like for example, for Kafka, the read implementation has a Kafka consumer code. And for write implementation, it will have Kafka producer code. So in Gimel, we have used a combination of open source connectors and some of our in-house implementations for the storage connectors. So this is how a Gimel SQL is parsed and converted into a Scala code behind the scenes. Okay, now let's look at the Gimel Thrift server. Now, as most of you might be aware of Hive Server 2, which is a long-running service used to run low-latency queries on Hive. This is built on Apache Thrift concept. And Spark Thrift Server is an extension to Hive Server 2, the difference being Spark as a compute engine instead of Hive. Now, with both of these services, we get a power of running low latency queries, but still we don't get an abstraction to read or write from different storages. That's why we added a support of Gimel into Spark Thrift Server, so that with their combination, we get a power of running low latency queries from Thrift Server and the power of reading from any data storage from Gimel. In Gimmel Thrift Server, we also added some PayPal specific features and integrated it with our unified data catalog. Okay, now let's look at a scenario where a user wants to read data from Hive through SQL. Now, in a normal scenario, user requests for a Spark session from the cluster, and once the user will wait for the Spark session to be created on the cluster, and based on the cluster capacity and traffic, they might have to wait for a couple of minutes. And once they get the session, the query gets submitted and they're able to read from different storages. So overall, this process has some latency in running the queries. And also some external applications like Node.js are not able to access these data storages because they need to connect to the Spark cluster in order to get a Spark session. Okay, now let's look at how it looks like with Gimmel Thrift Server. So here, user can just submit a query to Gimmel Thrift Server, and with the long-running Spark session maintained by the Thrift Server, user doesn't have to wait for creating a Spark session now. Instead of that, the query gets submitted to the already started Spark session, and they are able to read from different storages right away. With this, the external applications like Node.js can also connect via JDBC to Gimmel Thrift Server and are able to read or access these big data storages very easily. So this is how, by combining the power of Thrift Server and Gimmel, we get to run low latency queries and we are able to read or write from these data storages using SQL. Okay, let's look at the next steps. Over to you, Deepak.
Sure. Can we just move over to the next slide? Cool. Thank you. So PayPal is on the path to cloud. So we are looking to add support to all these different stores that are in the public cloud. And as we expand support to these cloud storages, we want to make sure we still keep the SQL community completely taken care. So we'll need to make sure the SQL support that Anisha walked us through is available for these different stores that reside in the public cloud. And moving on, as we continue to abstract the access, one of the problems that we have started facing is a lot of users don't know exactly what happens when you fire a SQL on a terabyte system or a petabyte system. So we need to start adding query guards and preempt runaway queries. So we'll need to spend a lot of time on tuning the queries and applying guards behind the scene. And on a visual side, we would like to expand our catalog connector support to Google's data catalog so that the community beyond PayPal can make use of either Hive catalog or Google's catalog, or maybe AWS Glue or something else in the future, so that it's not restricted to specific set of catalogs that we are supporting in PayPal. And as we move on to support these different kinds of stores, one of the big realms missing in Gimel is Graph. We want to make sure that we simplify the access for Graph as well. With the emergence of Neo4j in many different realms and Spark having a good support for Neo4j, we are looking to hopefully add Neo4j access via Gimel. That way the Graph access is also simplified, and maybe hopefully in the future we can add SQL support to it. And last but not least, as things are really heating up on the ML NLP side, we want to make sure the integration with ML and NLP is tight in Gimmel, and there is a rich support in the Gimmel APIs, so that the data access that is really simplified can be very easily integrated with some of the ML workloads. With that, we would like to end this session, and for anyone who is interested in chatting with us, we would like to take it forward in our Gitter chat, or we will be available in the channels in this conference. And please visit gimmel.io if you're interested in either using it or contributing to Gimmel, and we can chat outside. Looking forward to it. Thank you.
I'll just add a special thanks to our awesome Gimmel team that is implementing all of these features. And we are really on the path to democratize data access in a safe, secure, and very flexible way to all of our users. I'll see you then in our community room. Thank you.